So, Daniel Valente is from Federal University of Mato Grosso, and he will talk about quantum cloning in waveguide quantum electrodynamics inspired by non-equilibrium self-assembly. So you have 40 minutes.
Okay. So, well, first of all, I'd like to thank very much the organizers for inviting me. It's a truly honor to be here, and especially because of Professor Victor Dodonov anniversary. So happy anniversary. And well, the title of my talk somehow mixes terms that may be familiar to some and other terms that may be not so familiar, because we are from a quantum community, and then the first line has words that we usually see in the quantum community. Quantum cloning in QED, in this case not cavity QED but waveguide QED, may be something that sounds familiar. Non-equilibrium self-assembly, it's far less familiar. So I took this picture on purpose because I think this gives a little bit of the taste of what I'd like to talk about. This picture, I took it 2 days ago, right outside this auditorium. So when we go out and we take to our right side, we see this piece of art. And I don't know if you guys noticed it, but it called my attention because of the following thing. This, for me, it looks like an origami. It's a piece made of metal, and it's folded in a way that is obviously non-random. To get to this kind of configuration from random material, from raw material, it's not so easy. And to do that, we have to apply lots of mechanical forces on the system. We wouldn't get there only by heating the system. We have to perform work to achieve this kind of assembling. But the other thing that is very important in this picture is the tree right here, because this tree is also a very special configuration of the constituent parts. If we blend this tree, it will not look the same at all. So both things are very special configurations of its constituent parts, and the key difference, and beyond that, both of them had to absorb a lot of work to get to this configuration. So in this case, we have to perform mechanical work, and the tree has to absorb a lot of electromagnetic work to get there. But the difference is that in the piece of art, we have a lot of human intention. So the directions in which the forces are applied are very engineered. So people have intentions. And in the case of the plant here, the sunlight who drives the system to this configuration has no intention at all. So in this sense, we call this an example of a non-equilibrium system, because it has to absorb work from its environment to keep growing and keep making flowers and unfolding its form like this. But it involves no human intention. So in this sense, it's self-organized, it's self-assembled. So the thing I'd like to bring to the discussion is how general is this kind of effect. So how can we generalize this biologically inspired process where we have a source of work that has no intention in the first place, so that states are naturally arising and emerging that makes things interesting, even in non-biological matter. So I'll start with some classical examples of experience that I like really, that I think are really attractive, at least for me. When I saw it the first time, I found it beautiful. So I tried to open a video here. Does that work? It's working, yeah. I simply don't know if that is working also in YouTube. Is that? Okay. So this is an experiment made in the self-assembly lab at MIT, and they show a table that has a certain pattern of oscillating pattern, and people throw raw material, which is macroscopic, and then some lifelike properties start to emerge. So there is what they call growth and encapsulation, like a 2D cell. Of course, it's artificial. And then the cell, at some point, randomly splits, and it may split in two cells. So this is what they have called cell division in this kind of system. So this, I like this video because it's a very simple and beautiful example of here and back again. Okay, so it's a beautiful example of some self-organizing or self-assembling system that is driven by work. And this work has no intention, so people are not putting the spheres in the right places. What is also interesting here is that sometimes replication happens, this artificial replication happens, and the other way around happens too. So it's kind of reversible. So it's weird because biological cells don't merge back to get in the state before replication. It's you don't expect a bacteria to replicate and then come back to a single bacteria. So that happens because this is not sufficiently dissipative, so it's not so stable. So it comes back to previous states. And this other experiment shows that when you increase dissipation, the system stabilizes in these self-assembly lifelike states in the following sense. So here it's another example. It's a classical system where we have some metallic beads, and they are put at random there, and they are immersed in a viscous fluid. And when the tip has some electric difference potential, it starts flowing electric current through the system. So this ring here is set to 0 voltage, and this is a positive voltage. And after some time, the system kind of self-organizes to this tree-like or worm-like setting. And this is the authors also call attention to the fact that if they move the tip, the worm goes after it, as if it was looking for this energy consumption that is available to him. So these are examples of non-biological material that self-assemble in interesting ways that remind us of biological living things. To start making more mathematical sense of it, I bring here one theory that called my attention. I don't know if there are other theories, so this is what have been called by the author the dissipative adaptation. It is also a classical theory here. This has been proposed by a guy called Jeremy England, which was also at MIT at the time, and he builds on theorems like Crookes' theorem and Jasinski's theorem that have been cited here. And his idea is to try to generalize Boltzmann distribution for non-equilibrium processes. So his idea was thinking of generalized systems where we have fluctuations, thermal fluctuations, but also sources of work. And those sources of work would drive the system preferentially more to special configurations. So when we don't drive the system, they may assemble in states that are dictated by the final energy. But when we start driving the system, the final energy is not the only thing that matters, but the history from the beginning to the end starts to become more important and starts to play a role to bias some states to become more typical, whereas they would be highly atypical in the equilibrium configuration. So he proposes a rate of trajectories between a certain configuration of the system initially at equilibrium, and the system has lots of final configurations that it can reach, and the path, time-dependent path from this initial state at thermal equilibrium to a final state is, in his theory, given by three terms. The first one we immediately recognize as the Boltzmann contribution. Of course, Boltzmann will not start being important because of out of equilibrium physics. It's there. But it's not the only thing that matters, because here we also have the probability of the states coming back to the original states. So this is important because there are, we can think of a huge phase space where these systems are jumping over barriers, and there are barriers that are really low in energy, so the system can go there and come back very easily. So the system will visit more states that are also easy to come back again, because the barrier is low, so it will visit there. But there is a third term here that somehow puts into mathematical terms what I was trying to convey by intuition and by some experiments, which is the work performed on the system starts during the trajectory, because here it's important, the work is computed starting from a given state and ending at another given state, and the work performed by the external energy source on the system bias the probability of that particular state arising. So that's where self-organization comes from, if we are considering a source of work that not necessarily has a human intention, someone intentionally engineering the system. So this is what Jeremy called the dissipative adaptation, and the idea of adaptation is, of course, biological, although the dissipative part is much more physical. And the idea is that when the source is there and has no intention, the system will try to look for new minima, and then it will adapt in places where these probabilities are maximized. So the adaptation here is some generalized form of biological adaptation. He's always thinking about biological systems, and I like this point of view because I think it's inspiring. So now comes what I started doing here. In view of that, can we do this with quantum systems? So can we just take quantum systems, give them enough work, and they self-assemble, self-organize into states that are specific, that are maybe useful for some task, or that are interesting just because it's rare somehow? So the simplest quantum system that we thought about that could somehow mimic this effect led us to these two equations, which were surprising to us because actually I thought England's idea would be simply wrong in the quantum case. That was my hypothesis, and I proved myself wrong. So this is a case where, as I'm going to show in the next slide, we have the driving given by a single photon pulse. So it's a quantized source of energy, non-equilibrium energy, driving a single three-level atom. I will get into details later, but I think the most important thing to start discussing here is the fact that everything is at temperature equal to 0. There is a bath there, I'm going to show that, but it's temperature 0. And when we come back to England's result, it diverges for 0 temperature. It's highly classical. So these comes from a hypothesis that does not use Crookes theorem. So the fact that we have these kinds of analogies indicates to me, at least, that maybe the idea of dissipative adaptation is more fundamental than Crookes theorem used to derive it in the first place. The other thing that is that has been critical for me is that the energy source here is quantized, so it has quantum fluctuations in the state of the electromagnetic field, and this I thought that could produce some kind of coherent transition that would allow the system to jump between states, like tunneling, something like that, without absorbing work. And that's another thing that is important here when we look at these equations. And there are also these rates here, which are spontaneous emission rates, which come about naturally and have some analogy with the kinetic part of the classical equation. So this is the main result that I'd like to show you. And now I'm going to enter into technical details of how to derive it, and then an application of it. The part of quantum cloning will be an application of this result, but this is the main point here. So this model that I have just shown you was inspired by these kinds of systems that are pretty recently performed in the lab. So here we have two examples of quantum electrodynamics performed with waveguides. Here we have photonic material, so light will propagate in this channel here, and we can embed a single quantum dot in there, and it can emit single photons, absorb single photons, and well, there are many other systems with semiconductor materials that perform these kinds of single atom, single photon interaction for propagating photons. And also we have here superconducting artificial atoms, which also can be the platform where these kinds of models can be performed. So now into the model. So here we think of the field level system, for example, the quantum dot, and we can excite it with a single photon pulse. The pulse here is very important because it has a finite light limit that we can change so as to affect the probability of transition between states in this atom. So this photon is defined as a sum of frequency, and we take this sum of frequency to the infinite limit. So it's a continuum of frequency modes here, and we can choose these amplitudes for each frequency mode of the single photon. And we can also describe it by a real space wave like this. So the amplitudes have a Z and T representation. So this amplitude is this one evolved in time, and this is the spatial part. And the coupling between light and field here is, again, a sum of many interactions between each mode of the electromagnetic field and this field level atom. I'm also considering an integral in frequency space here. And it looks like Jennings-Cummings model, so it is indeed, but for a continuum of frequencies. And my very simple self-organizing process is thinking of an atom initially in a mixed state, and I send a photon hoping that it will be in a pure state in the end. Can I get it? Yes, but only if the photon is really in the highly monochromatic regime. For finite pulses, I have in the end some mixture of these two stable states. And I can compute this probability of starting in this configuration and getting to this. And the way I do this is deals with the probability transition of starting at state n and achieving state k at time t. So this is the n represents an atomic state, and 1a is the photon pulse. Here, this unitary takes into account a continuum of modes. So, of course, my universe here is taken into account all the frequency modes and all and the atom as well. But when we trace over the environment, the spontaneous emission rate appears naturally, as in any system plus reservoir approach, and we get the transition probability depending on the decay rates gamma B and gamma A, which are related to the couplings, to the square of the couplings between field and atom. And here we also compute the work, right? Because we are interested in sending light to a system and seeing it self-organizing, like inspired by the idea of biological processes. So we perform the work of the electromagnetic field quantized in this single propagating photon mode on the electric dipole of the atom. So we take here something that looks like a classical definition, but this classical definition, I think it's important as a mnemonic way of looking at this, but it is Heisenberg picture, so it's fully quantum way of quantifying the amount of work a single photon pulse does in the atom. There is also a Schrödinger picture for this work that we can show, but I think this one will be the most significant way of describing it. And then we can show that by no matter the pulse that we use, we can always relate the probability of the system starting at state A and arriving at B for long enough time with the work done by the photon on the atom. And the reverse pulse has no way of getting the state back again to the initial state, because the photon is polarized in the A mode, which only interacts with the A to E transition. So if the photon starts at B and if the atom starts at B and the photon come backwards, it will have an orthogonal polarization which will not interact with this transition at all. So that's why a 0 comes here. So far, so good. We have just found a relation between the probability of achieving a specific state that is special in some sense. In this case here, it's pure state, due to the fact that we are performing work on the system, but the source of work has no intention to move, to do exactly what we would want it to do. So it's what we are assuming as a self-organizing process in a non-equilibrium quantum system. Now I'd like to go a step further, if I have time, maybe 5 minutes, and play with this in I'd like to go with this analogy with biological systems a step further. So the MIT experiment was also trying to play with this idea of replication, and this I'd like to do this as well with quantum systems. So I can think of making now 2 waveguides and putting a series or a line of quantum dots in there and trying to replicate the state of one of the chains into the state of the other one due to this driving of the system. For this, I assume something that looks like a Casimir-Polder Hamiltonian, so it's dispersive, like easy interaction. And this has been assumed here so that whenever the state of one of the atoms is A, it affects the um, the resonance condition of the other atom. So this is uh, what this sigma z here does. It affects only a transition. And then I can send photons at polarization B and prepare all the atoms in B state. So it's like an empty state. So it has no special information encoded in it. But the first line will have some sequence of states that may represent some information. So I'd like to replicate this state into this state. So I'd like to start with this state and end up with a state for each atom here that is exactly the same as the state of these reference chain of atoms down here. And so it's the same idea again, but now I have this Ising-like coupling mode. And when we send the pulse, we can find the probability of transition between an atom starting at state A. So this one will start at A. The one that I would like to replicate to copy the state will be at B. And I'd like to find the probability of finding both of them at state A, given time t, after the photon pulse has gone through. So time's long enough compared with the time window of the pulse. And then we arrive at this expression here, which has a Lorentzian term, but other terms here. And delta here is the line width of the pulse. So the inverse of delta is the time spent by the pulse interacting with the atom. So when delta is really small, the pulse is monochromatic, so the pulse is really long in time, so it interacts a lot with the atom. And then these terms here go to zero, this term here goes to zero, and if the photon is at resonance with the perturbed frequency of the mode of the atom, this delta will be zero, and we have probability 1 to do this transition. And whenever delta is not zero, we have a finite pulse, the probability of replicating is not ideal. The most interesting thing is that whatever the size of the pulse and whatever the shape of the pulse too, here I take a Lorentzian spectrum, but we could think of Gaussian spectrum and square pulses and any pulse that we would like. This relation keeps coming back again. So the dependence on the probability of this adaptation to this shaking of the atoms is all the times related with the average work observed from the work source. So this idea coming back again that we put work to achieve special states of some system, even if the work source is not designed, is not engineered to perform exactly that state. So it comes back again here as a quantum dissipative adaptation again. So I think that we can go back. Well, before concluding, if I have time. So here we have another effect that we can always have some kind of mutation in this replication, and this comes from the fact that whenever the state of this atom is in B, the photon will be out of resonance with this atom here, which is at B, and we'd like it to be kept at B. So we think out of resonance, it will just go through because this term will be very large, because then the frequency will change because of this J coupling, and then there will be no transition. However, even an off resonance photon can perform work, although a very low amount of work on the atom, and can perform a transition very occasionally. So if we make an analogy of this sequence here as an artificial gene, and this as an empty gene that we would like it to replicate the first one, there would be
2
some
minutes left.
mutations. So now I conclude because that's it. So in summary, what I'd like to have convinced you is that the idea of dissipative adaptation suggests a bridge between classical and quantum non-equilibrium self-organization, and that it, from an application point of view, it may be a route for us to look for more self-organized quantum information processing. Here I chose cloning as the best analogy I could find with biological systems, but which take dissipation as a key resource, because this is how biology works, and the bacteria are very good at sensing and performing a lot of kinds of information processing. It's an open system, and maybe we could look for another route to quantum information processing that is based in these ideas. And I end with a citation from the Nobel Prize of Medicine, Albert Szent-Györgyi, from 1937, which once said that life is nothing but an electron looking for a place to rest. So if that is the case, any device that is non-stationary is somehow alive. So can we make it even more alive? That's my question. So thank you.
Let's thank the speaker.